Welcome everyone to this session on using numberless prompts to deconstruct worded questions for year 2 and year 3. It's very common for children to find it difficult to apply their understanding to break down worded questions and to see the maths structure, the underlying structure of a maths task, to apply what they already know to different contexts. I wanted to have a look in this session at using a specific technique, the use of numberless prompts, to give all children success in breaking down worded questions and to really focus children in understanding the process of answering a question rather than being over-focused on finding answers. To do that, we'll look at how information can be layered and introduced gradually so we don't overload children's working memory, and how we can focus children on specific points of learning or key differences between correct and incorrect when they're breaking down worded questions. We'll go on to have a look at how we can add challenge and give children opportunity to be really creative as well and see little variations between different types of worded problems. There'll be lots of examples that are obviously specific to year 2 and 3, and this will allow you to have a really consistent approach to how you actually teach the use of worded problems and build children's understanding of worded problems. It will give all children success, and we'll see how all children can be challenged. So to start off with, I want to ground what we do today in this understanding of the relationship between working memory and long-term memory as it applies to answering worded questions. So we've got a very limited working memory with which to process new information or to process information, and that can get really easily overloaded. And we've also got an enormous capacity for storing new learning in long-term memory, and the schemas in our long-term memory, if they're well developed, we can bring them into our working memory and they lessen the burden on working memory. Now, where it comes to worded problems, I would say they come with a heavy cognitive demand by their nature. There's a lot of processing to do, reading information to do, to think about what do I then do with all of this information? How does it relate to my other mathematical experiences? So I would think, how do we limit the demand on working memory if we're going to give children higher success in worded problems? And also, I think the mistake that I've made throughout my career is not being explicit enough how different worded questions link together. Because we know where children need to apply their understanding from their working memory into the long-term memory, they need to be able to connect that learning to their wider understanding of mathematics and be able to connect their mathematical experiences well. And I think by having, which we'll get to, related maths problems together with similar-ish structures, children have more success then in tying together their understanding in their long-term memory of different structures of worded questions. Now, to start off with, I want to use my 2 or 3 favourite examples, these two and another favourite example, just for explaining the basis for numberless prompts and what they can look like. I've talked about these on training many times, so I'll be relatively brief here. But just to say, my 2 favourite techniques to achieve this are making a question numberless, which I'd simply define by covering up the numbers in the question, like the top left example with the toys, and asking children what the possible numbers could be, or for them to create their own examples. So children think about the structure of a question before they come to actually find one definitive answer to that question. Or, and we'll look at different contexts in which this applies, giving children a question where the question and the information required to answer that question are hidden. And I tend to go the question hidden by a red box and the information covered by a blue box. And asking children what possible questions could be, and then thinking, well, what information is required to be able to answer that question? So 2 straightforward techniques so that children explore structures, but they're not having to get to the point where they have to answer the question immediately and have almost that threat or that possible victory too soon, but they actually have to delve into the structures of the question. So we'll explore these principles in different contexts. And this is actually a question from the White Rose Progress Check Year 1. And again, just a really simple manifestation of just by covering up some of the numbers in the question. So Ollie spends a certain amount on a teddy, he pays with a certain number of coins, and then saying, so how, give me a possible answer. And then I can narrow down slightly by showing Ollie spends 30 pence on a teddy. And then again, I might say, all right, I want 3 possible answers. Or let's say a child says he pays with 5 coins. Have you found the only way you could pay with 5 coins? But having multiple possibilities before we get to the point where children see a whole question. And at this point, hopefully they've really deeply understood its structure. Now, the research basis for this. So this is removing opportunities to calculate, improve students' performance on subsequent worded problems by Given and Stigler. And I found this really fascinating. When students are presented with a mathematics word problem, and I don't know if this resonates with you and your experience, their first response is often to try to compute an answer, even before they have tried to understand the problem. Studies of expertise have shown that experts attend more to the underlying structure of a problem, whereas novices rely more on surface features. And the surface features might be the context, say, that we're exploring. Expert problem solvers typically spend more time thinking about problems and trying to understand them than do novices, who tend to immediately execute a solution. So again, I don't know if you've ever seen this, where children just see numbers, they think they immediately jump to try and do something in almost a kind of panicky response, without thinking about and unpicking the deep structure, which is a routine we want to get children in. And I believe the techniques we're going to share will really help to do that. Well, again, what does that look like? Let's go on in this study. So it gave examples of questions that it would call calculable, in that you could calculate an answer, and non-calculable. And so if I give you a moment to read these 2 examples, and again, if I move on too quickly for you, then please pause the video. But you'll notice the difference between these questions in terms of one is calculable and one is non-calculable. So if I give you a moment to read them and think about their different structures. And again, if you need a little longer, please pause the video. Now, again, in this investigation, I'm not necessarily suggesting using these exact prompts, because I think there's a lot of processing to do in terms of the reading here as well. But then we have a look at the impact of these 2 groups for the children who answered the calculable problems, like the blue one, and then the non-calculable problems, like the green one, in their subsequent performance. And what we see is that participants who explained the non-calculable problems performed significantly better on the transfer test than participants who explained the calculable problems. So they were then given calculable problems afterwards, and we had a look at the impact of what had happened prior to them seeing those questions. We hypothesized that the mechanism at play was a reduction in instrumental thinking and an increase in relational thinking. This key idea that children having to think about the relations of the task before they get to the point that they jump in to the actually performing those calculations. And that is the basis really for the numberless prompts and the impact that I think it can have, that and that I've seen. And also looking at how we can do that to really minimize the load of children having to process that information as well. So hopefully those 2 things will come through with all the examples that we come and share now, and you'll be able to see how this outworks in your classroom. Let me give you a moment to read this example question here. So again, this is a structure of a task that I think you can get a lot from. And as a one standalone question, I have a lot of information to read and processing to do. And then the kind of net result I could get if I use this in isolation is the value is almost 1 question. But what I would suggest is, how can we get children to explore this structure first in open-ended ways, give children relatively higher success first? How can we create lots of little variations on it so children can see the difference between if the numbers change slightly, and build this really strong interconnected understanding of this as a structure, rather than doing all that processing for the value of 1 answer. Now, my first suggestion would be making the prompt numberless and potentially trying to minimize the processing. So this would be a numberless prompt that children could have, So Jen had a certain number of sweets, Zara had a certain number of sweets, and then Jen gave Zara a certain number of sweets. Who has the most sweets now? And children could at this point give a possible answer, or you could model that, showing what this could be, how many Jen could have started with, how many Zara could have started with. And we explore that structure. And of course, we could do that practically as well. Now, from there, if I was looking at essentially a non-calculable problem, what I might do is phrase the prompt in this way and ask children to come up with what the number of sweets could have been, what could have happened. So if I give you a moment to have a look at these two examples. And so this enables us to explore the underlying structure. And again, if I come up with a possible solution where Zara now has more sweets and where Jen has more sweets. So hopefully we could see that if we were thinking back to that original prompt, now children have explored that in open-ended ways and hopefully would have higher success. Now let me move on to a little sequence of questions here. And you can see that the differences between the questions are or when you have time to read them, the differences between the questions are deliberately very small, so that children will be able to appreciate when this one aspect changes, it has that effect. Now, if I could give you a moment to pause the video, have a go at answering those questions, and then have a think about the effect of having such small differences between the questions, as opposed to if the context changed, or even if all the numbers changed. So pause the video, have a go at that, and when you've done that, then we'll resume. Okay, and let's have a look at the effect of that variation and potentially a child's experience. So Jen had 20 sweets, Zara had 8 sweets. Jen gave Zara 3 sweets. Who has the most sweets now? Well, excuse me, Jen still has the most. She's got 17 and Zara's got 11. Now, the difference is smaller, but it's still a significant difference. So the next question, only one number changes. Now, Raj has 20 sweets, but Tim has 12 sweets. And Raj gave Tim 3 sweets. And what do we see now? Now, this difference between 20 and 12 is 8. But by giving 3 sweets, we still have, Raj still has more. The person who originally had more still does, because changing those 3 isn't enough to bridge that gap of 8. And that might help children to see the structure now of what might do that. And then again, we get to the next question, where we have the same numbers of sweets, obviously different names of people. And I try and make the names CVC names, of course, to make the reading as minimal as possible. And also, out of interest, I try in each question to have either all boys or all girls, because otherwise children's attention could go on, well, I want the boy to have more, I want the girl to have more. Don't know, again, if that's your experience. But anyway, let's go for Cam and Jack. So what do we see now? Still this difference of 8 sweets originally, but if Cam gave Jack 5 sweets, wow, that's generous, then actually now we more than bridge that gap. So now Jack has more. They have 15 and 17 each. And notice how that little variation highlights the structure more than if they were just random questions. Now, from there, I would say there's great opportunity for children to create their own example questions as well, and have this opportunity for creativity and really apply their understanding of the structure. I've written an example prompt, write a question where Jack ends up with 5 more sweets than Cam. Now, going back to that original question, so much can be taken from one prompt. And hopefully there's examples that you can apply directly in your classroom. But again, I always encourage people to think, how can you take different worded questions and think, I can get so much from this? And hopefully you'll feel empowered to do that as we go through. Here's an example that I've used in training recently, and I found some amazing responses from different teachers of how it could be, how this could be used. So there are 100 grams of chocolate chips in the bag. Sita uses 25 grams, Ben uses 35 grams. How many grams of chocolate chips are left in the bag? And again, I imagine if we give children this, some will be able to answer it, some won't, and will have, you know, relatively low success. We've got challenge in the calculation that's involved, as well as understanding the structure. Children might not necessarily know what it means if CETA uses chocolate chips rather than eats them. We have them in grams rather than as individual chocolate chips. And we are starting at a high level of challenge. And the structure for this task that we want children to see, I guess, is this, that there's a whole number of sweets in the bag. There are two parts, which is CETA and Ben, and we're looking for the third part, which is what's left. Now, if I'm taking this as a structure, if I reframe that and make it numberless, I can actually explore different structures. And I could decide that rather than grams of chocolate chips, that I go for the number of chocolate chips, and I could represent it practically using this same numberless prompt. And I'm trying to minimize the information that's there for children to process as well. So we can focus their limited attention on the actual maths in this context. If I introduce the question like this, we have the same structure of question we had before. Perhaps children will find the level of challenge in the calculation different, easier, more accessible at first. But equally, I could use this same prompt to create a question with a different structure. And I could create multiple questions here by seeing how many CETA has, how many Ben has, and that there are 12 left in the bag. I like there to be one number that's significantly larger than the other one, which may lead children to believe that that larger number is the whole, just because it's significantly larger as well. And that's not the cue that helps children to see the structure of the question, because the numbers are very similar. And equally, I could change the structure. And this was, again, just from a suggestion that I had from a teacher looking at this task, which I loved. So it could be there's 100 grams of chocolate chips in the bag, and CETA actually has a quarter, so we introduce fractions. Ben has 40 grams. If I was looking at adapting and creating, as well as adding the challenge, creating a variation on this task. So we can take this same context but just add this aspect to this same context as well. So hopefully less processing in one way, but focusing children's thinking on that specific change. So again, I wanted to look at the effect of variation, and in this case, slowly increasing the level of challenge for children to be able to access questions that they may see as more difficult, and also for being able to appreciate the difference in the change in the wording or change in what's being asked to do in each of those steps. So again, if you could pause the video and have a go at that, and we'll look at them in a few moments. Okay, and again, whenever you're ready, if you play the video again, and hopefully you can see from question 1 to question 2, that will perhaps help children to see the relation in the actual calculation for question 2 and apply essentially the bonds to 10 to a bond to 20. And then in question 3, we introduce another part. So rather than a part whole, there are 3 parts in the structure of the question. And then again, from there, for example, I could introduce the fraction, or it might be that I ask for that I give 3 parts and ask children to calculate the whole. And again, one of my favorite ways of extending is always to ask children to see how they could extend that sequence. Maybe they could do that by changing one of the numbers or having a different structure of a question, but brilliant opportunity to open up discussion. Now, let me give you a moment to have a look at this question and to think about what could you do here with this prompt to get more from it than the value of just one question. So if you could pause the video there and have a think about what you would do here. And again, let's have a look. Now, I share this not to say that this is the correct thing to do, but just to say an example of where you could go here. Now, my preference is generally to lessen the challenge in the calculation, to focus more on the deep structure of the question. And I could always change the level of calculation in the numbers that are used if I saw that as being an important thing to do. And then again, the structure that I like to use is hiding the question in a red box and the information that is required to answer that question in a blue box. Now, if I, for example, ask children to say, what could the question be here in this context? What are the different possible questions that could be hiding underneath that red box? We could come up with questions like those there, which I'll give you a moment to read. And in exploring that list of questions, what we could then ask, well, if that's the question, what must be hiding underneath the blue box? What information would we need to answer that question? Again, enabling us to focus on structure. So if I give you a moment to think about those three examples. And what you might notice is that actually question 2, how much money does Nima have left? And question 3, how much change does Nima get? Could essentially be the same question. And in seeing that, children will actually come to experience the effect of that wording, and actually that wording relates the same structure. Again, I could represent that, for example, with a bar model to show that both wording could represent the same structure. And again, if I was looking to add the challenge, it could be that we explore questions like those three, and then think about how what would be required to answer, what information would be given to enable us to answer those three questions. So again, if I just give you a moment to read those three examples. And again, from there, I can manipulate the level of challenge in the calculation, for example, if I wanted to, with the numbers that could then be introduced. But I think a great way of taking one prompt and getting so much from it, and I find it such a flexible technique when I see different worded questions of whether it is thinking I'm going to hide the numbers or will predict what the question could be, and some contexts lend themselves more to this structure than others. But hopefully this is really going to arm you with so many tools that you can use for exploring different worded questions. Another example where I might use this technique. So here's the cost of some items in a shop. And then again, I could say, well, so what could the question be here? We could generate different possible questions. And let's say I showed, well, let's say it was, how much does it cost? What information do you expect to see under there? What will we need to know to be able to answer that? And again, we could see, Sam buys 2 bananas and a drink. How much does it cost? I must know what he buys to work out how much it costs. How much change does he get? What do I need to know this time? And we get to, well, what does he buy? And what does he spend? I'll need to know here. Of course, what he pays with must have a greater value than the cost of what he purchases. How many bananas can he buy? What information do I need now? It's the amount of money that he needs. And again, if I was extending, I might say, well, actually the answer is 3 loaves of bread. What must the question be? And what information is needed to answer that question? So if it is the answer 3 loaves of bread, it might be, how many loaves of bread can he buy? Would need to be the question. And then I could say, okay, well, what are the different possible things that could be underneath the blue box? Is there one possibility? Are there different? Let's say we have a look at, Sam has £1.50. And what else could that value be? And so on. So many ways that this can be applied and explored. And again, I provide a little sequence of questions here to have a think about how, with those small differences between the questions, how children can use one to help them to answer the other, how it might lessen the barriers at first to actually performing those calculations, and then with this opportunity to extend at the end. So again, I just kind of invite you to read that little sequence. And again, to note, for example, the difference between question 2 and 3, where we don't need to recalculate the cost of the items to then calculate for question 3, how much change she gets. And again, with this extension of the opportunity of almost opening up the mathematics for children to explore. So again, principle that I always try and hold by. Now, I wanted to give you some time to think about the implications for you and potentially within your school as well. So the idea, I guess, of exploring one question structure in depth. Where would you find the questions from, for example? How could you do that? How do you see this being outworked in your context? Thinking specifically on what are the challenges, or what do you want to develop specifically in your children as well? And then creating sequences of questions from that using this small variation. How would you do that? Is that something that you could practice as a staff team, or that you would like to practice individually, or you feel is already a strength? But looking at those small changes that you can make to questions to create a sequence of questions where children can really see the connections that exist. Then thinking about the impact that we hope to have on the children. Which children? We hope that they'll experience more success, and the barriers to entry for worded questions will be absolutely knocked back. And then a real focus on question structures rather than on accelerating to answers. This quality that we see in expert problem solvers being something that can be opened up for all children. And then again, how we allow that scope for creativity, where children create their own examples, or again, see those connections really clearly. Now, I open up the discussion around logistics. So when and how often would we use this within a sequence of lessons? And that's a question I'm often asked. And I guess I would think, well, at what point do children have the expertise in terms of the calculation to access this content? How familiar are they with the context as well? Because the context might actually give them a representation and help them to understand the mathematics, because it might be a context that they're familiar with. But the thing that I would emphasize is children having experiences of problem solving that don't come at the back end that only some children experience. And again, the question of, well, how often would I fit this within a sequence of lessons might also depend on the relative strength of children in different aspects of mathematics. So if you see as this being a significant area to develop, then perhaps it's a greater weighting of time than if children are relatively strong here in comparison to other aspects of mathematics. Then the balance of whole class and independent time, what we do together and model together, and then children working independently on those sequences of questions. I like to be as explicit as possible for all children about showing those underlying relationships. And from the teachers that I've worked with, from their experience, they actually tell me that children whose attainment is higher really benefit, because they have to think about the deep structure in a way that they might otherwise bypass, because they just know the answer, and suddenly they have to explain about those structures. And that really tying into this question of differentiation as well, and how that works best, and what additional support might you give certain children to be able to access some of these deep structures, whether it's the time that's given, the pre-support to lessons, how you model the mathematics involved in different ways. And then the really big thing that I would ask you to think about is the consistency that you could have between classes. Because in my experience, introducing these techniques, initially, I've seen success. But the greatest impact is always when there's consistency throughout a school team. And that's something that I would really encourage you with. If children are used to numberless prompts, and that as a routine way of exploring worded questions, if they're used to predicting what the question could be, and then thinking what that information could be, and they get trained in that, we model that, what that looks like, then of course, if it's something that becomes embedded, the children just have so much more success. And you can spend relatively less time talking about and introducing the technique, and relatively more time just focusing on the content of that specific example. And that's something that I would encourage you with. How could we introduce these principles at first for younger children? At what point? How do you see that developing in your context? So again, lots to think about there. And so there, at this point, if you pause the video and think about those points. Okay, and I would love to be able to interact in terms of your thoughts on this, questions that you have. Please feel free at any point to email icmaths@hotmail.com, and I'll always try and endeavour to get back and I'd love to have an ongoing dialogue. Now, what I want to look at next is actually the importance of developing children's spatial reasoning. And what I will also do is just defer to the early childhood maths group, where I've kind of learned a lot from, being fascinated by myself. And if you want to find their full guidance on this topic, then again, if you go down, you can download the whole guidance document just there around the importance of spatial reasoning. So again, earlymaths.org/spatial-reasoning would bring you to this page. And let me just share some of the things that I think are highly relevant there. Something that I thought was really interesting was this. This question was given to children when they were 11, and we have these two different representations. So a balloon first rose 200 meters from the ground, then moved 100 meters to the east, then dropped 100 meters, then it traveled 50 meters to the east, and finally it dropped straight to the ground. How far was the balloon from its original starting place? And we have these two pictures. And the example on the left-hand side is a more abstract representation of the structure that a child has drawn. They are less consumed by the surface features and more looking to interpret the deep structure. The example on the right is a more literal pictorial representation, where the emphasis has been placed on the context rather than actually the mathematics that underlies. And the thinking is that actually, if children don't have that spatial development, then they become more likely to focus on those surface features of a question rather than visually being able to represent a deep structure clearly. And so how do we build those spatial skills as being a kind of key driver in children actually having success in understanding about deep structures of questions? Now, here are a few examples that I've come across or that I've done to try and do that. And one is this idea: if we want to build children's spatial working memory, one game that I've seen which I liked is the idea of see it, cover it, build it, where children there's some kind of a image that's constructed, it's hidden, children have to hold that image in their mind's eye and then try and recreate that image and then compare their creation with their visual representation. And again, a really key way of building children's ability to hold that spatial information in their mind's eye, which is so important as we go on in problem solving. Equally, and these are examples from the document that I cited, getting children to recreate with Duplo blocks these different images, which again kind of increase as we go down in complexity. And again, being able to compare and hold that information in working memory. Other examples include a mystery build. So one child builds some kind of an image on one side of a screen. They explain it to another child who has to try and recreate that, and they have to picture in their mind's eye what's being explained to them. And of course, we've got all the wonderful use of language in doing so. And then we have this image in our mind's eye, which we need to compare to the actual creation. Now, another example of how I've outworked this with older children is actually where we have images like the ones on the right-hand side, which one child can see, and they have to describe it to another, who then tries to do an accurate drawing based on that description. And again, we have all this great use of similar principle, great use of language, or the use of language, I should say, which we might need to also model. And then we have to compare the information that, what I see as in my mind's eye to that actual image, and really building those that visual spatial working memory. Similarly, this was an example which I like from an NCETM course that I attended online, where I've saying to children, how many shapes can you make with 5 cubes? Now, these are all, if you like, 2D versions, but then asking children to, well, I want you to categorize them in some way. And then how have they been, and we look at how have they been categorized when we see them in those 2 or 3 different groups. It might be based on symmetry, or it might be images that represent more of a 4 and a 1, or a a 3 and a 2, but for children again to be able to do that and play around with those ideas, but really building spatial skills as being really predictive again of children's ability to eventually problem solve and see these deep structures. A few other examples. The image of the leaves, it talks in the document about how if children only have to describe mathematical shapes, where there's less nuance between those shapes, the development of language isn't as great as if they have to describe differences in more nuanced shapes, like the differences between leaves that we see there. We have the image of the farmer and the fairy and the dog and the cat. Could we be able to describe what each character sees from their perspective? Again, building those spatial skills, what they can see and what they can't see. And similarly with the images at the bottom, looking at the same image from different directions and seeing what you see from one direction, what you don't from another, and being able to build all those wonderfully important spatial skills. So again, I encourage everyone to dig into that guidance, which I think is wonderful as well for further examples. Now, building from there, what I wanted to do, and the idea of visual representations, is consider variation and the use of visual representations as well. And looking at questions with different surface features, as in different contexts, and for children to be able to see the similarities in the deep structure and to think about how they could be represented, both with one-to-one items like double-sided counters, and then also with bar models. And again, the idea being that we go from having to represent with one-to-one items to a bar model being more of a general representation where we're not as tied in to a small number range to calculate within. And showing small differences between the structures of those questions in the sequencing of questions for children to be able to appreciate the differences between those questions. So really, I guess what I'm saying is, I want you to have a look at these example questions here and think about how would you represent these visually and show the deep structure and how the deep structure of the questions changes, whether that is how would you use equipment to do that, like double-sided counters, or how might you use a bar model to do that? So again, if you could have a go at that, pause the video, and then we'll and then play again when you've had the chance to do that. And again, I would emphasize the importance of all those, the importance of having those spatial skills to be able to create those visual representations in our mind's eye, of course. So there are 9 girls at the park and 5 boys. How many children? Well, first of all, I could represent all of these prompts with boys, girls, and children, and then talk about what we're actually being asked for as well. If I was looking to cut down on the processing to some extent. And then a representation, of course, what we have in this first instance, as we have these 2 parts, and the unknown is the whole. And again, if I was going from the items to a bar model, and again, I would do this actually practically, it's difficult to show under my visualizer with its size. I could then go to draw around those items, the 9 items, the 5 items, and then literally create the bar model from the counters for children to see that structure. Whereas there are 9 children at a party, 5 are boys. Well, what we know is that there are 5 boys, and then there must be 4 girls for there to be 9 children. And again, here, what am I asked for? I'm asked for how many girls. That's the unknown. And again, representing that in stages for children to see the stages of the thought process, I think is really important. Kieran Mackel's book was really enlightening to me for that. I've forgotten its name, but Kieran Mackel, you'll find it. And then again, we could draw around that information and represent that in a bar model in this way, showing the information that we're given, which is the 9 children is the 2 parts, 5 are boys, how many are girls? 9 children in the pool, 5 are girls, how many more boys than girls? Well, notice here the very similar structures of the questions in terms of the numbers that are used, but now what we're asked for is how many more. So actually the question follows the similar structure, but what we see is actually this time, this is the unknown that we're asked for. And of course, if I was representing that as a bar model, we have this difference. And again, I want children to appreciate the difference between the bar model in terms of what the unknown is that we're looking for, and making that really explicit. And this last example, there are 9 children in the shop. There are 5 more girls than boys at the shop. How many girls are at the shop? Well, this time, what do we know is we know the difference, 5 more. And then I've got to think, well, how many more children must there be? Well, there must be 4 more for there to be 9 children in total. Now, if I was representing that just with a bar model, I might start with more girls than boys, that difference being 5, and then thinking, well, what must those parts represent? And then what is that unknown value? But again, being really systematic and actually showing the bar model being created one step at a time. So children see, it's like we're uncovering the thought process. And we know that the way that our working memory works is we can process language and images simultaneously. So being able to have an image that corresponds with the language is actually very helpful and doesn't add to the load on working memory. In fact, it's great because we can activate both of those parts of our brains when we're doing that. What I wanted to do as well is just think about how and what can affect challenge in questions. So again, if I could just ask you to pause the video and have a think about here, the relative challenge in these 3 examples. Okay, and as well as the level of challenge differing in terms of the calculations that are involved, one thing that may differ in terms of the representations are the form of number that's used. So if we have a look at this first example, there are 9 children in the pool, 5 are girls. We can represent that very legitimately with one-to-one items, with one item representing one child. When we start to move between the different contexts, though, for money, that is less applicable and much more less applicable for time, if that made any sense. Insofar as time would more be represented by a continuous quantity. And it's a very abstract thing to represent. If I was doing so, I could represent it by the length of a line more legitimately, but I don't think you could with individual one-to-one items. So really important that children have experiences of different worded questions that include contexts where it's discrete amounts, whole individual things. It could be represented by counters, and also in continuous forms of number as well, like the examples, the second and the third examples that we have here. Now, I also just wanted to share this just as a suggestion for how lots of different problem-solving tasks can be made accessible. So this was an example I took from the White Rose Hub, and again, congratulate them for all their work. And again, if I was looking at this question that I saw, I essentially just covered up the numbers that are provided to ask children to come up with a possible answer using their own numbers. So if I give you a moment to think, like, what could the answer be, or what if you kind of come up with something, and I might add the challenge by saying they've got to be 4 different number cards. So again, you might need to pause the video whilst you do that, or but I'm going to keep going. And so maybe then I provide those number cards, and I say, you know, see if you can complete the challenge here using this combination. What did you start with? Which digit do you know? Oh, this can't go there because, or this has to go there because. And then this could be my way of building up to the actual original prompt. There we go, where we have challenge in a greater level of challenge in the actual calculation that's involved as well. And again, my general encouragement, I guess, would just be to look at lots of kind of worded problems that you come across and think, is there a way I can lessen the barriers to entry here, whatever it is? Can I take the numbers out of this question? How can I create different versions of the same prompt? So hopefully you as a teacher can get more from less, and it will also help children to have higher initial success in problem solving. I'm a big fan of having higher initial success and then believing children will persevere for longer and see connections between these different kinds of tasks. Let's have a look at one of the numberless prompts that I use most frequently, which is people camping, people per tent, tents needed, and asking children to give a different possible solution. It might be a story like, we went away camping for my brother's 40th birthday. So how many people could have been camping? How many per tent? How many could there have been per tent, and how many tents needed? And the children will often come up with a response like this: 12 people camping, 4 per tent, 3 tents needed. And I might say, represent that with counters. And we might have a representation like this. And then say, I might take an example that we've seen in the room and work from that example, but tweak it ever so slightly. So let's say we change what we have into this. Well, let's say, well, what if there were 11 people camping? What now? And I remember a child saying, well, 11 people camping. This was before the COVID pandemic. 1 per tent, 11 tents needed, and we have a socially distanced camping trip. But let's say, okay, well, let's say there's 11 people camping, but there's still 4 per tent. How many tents would we need? Have a think. What's the same and what's different? And we come to see that actually we would still need 3 tents, and we can get to, well, how can the number of tents required be the same? And noting that it isn't always the case that this number is this multiplied by this. And then again, I could go to the kind of the furthest extreme and go for, well, how about we go to 9 people camping, 4 per tent. And again, here perhaps we'll see that we would still need those 3 tents. But if we went down to 8 people camping, 4 per tent, then we'd only need 2 tents. Now, if I go back to here, something that, again, for example, I could ask children to explore, if I was deepening, is we could say, right, well, this picture represents 12 people camping, 4 per tent, 3 tents needed here. But actually, for my brother's 40th birthday, there weren't 12 people camping. There were, wow, he's got a lot of friends. There were 24 people camping, and we actually had 8 per tent, so they were big tents. How many tents were needed? And so we're exploring that the difference between 12 people camping, 4 per tent, and 24 people camping, 8 per tent. And of course, we'll see it's actually the same number of tents in the end, but using that little variation to, again, explore those big mathematical ideas. And then I could go from there, for example, from looking at a combination with different possible answers, like 8 per tent, that there were 8 per tent, 3 tents needed. How many people could have been camping? It could have been 24. It could have been 23. What's the fewest number of people it could have been? So many different possibilities that can be explored there. So I found that a really flexible prompt. The other reason I like that prompt is it is like you would naturally have it, that you can have tents of different sizes. Whereas if we're talking about, let's say, egg boxes, they would tend to be in 6s or 12s. So I always think that's a kind of nice prompt that I like to use, particularly if it's familiar to children's lived experience. Now from there, that could lead in to the use of small difference questions, which I talk a lot more about in the embedding reasoning routines training. And again, looking at and modeling those little differences that happen with the small changes in a question. So again, deliberately small differences between questions. So 18 people camping, each tent fits 3 people, how many tents are needed? Then again, I could have a visual representation to show that, it is 6 tents. And then I could actually articulate, well, what's the same and what's different about the next question, get children to really spot and explain those relationships and seek them out. I noticed that there's double the number of people camping and there's double the number that fit into each tent. What do you expect? And for children to form an expectation, which will hopefully either be confirmed or they'll get a surprise. It's not what they expect. And then they'll have to think about, well, why was that? And again, then we have the visual representation to show it's actually the same number of tents. And then what about when there's 31 people camping? What's the same and what's different? Well, it's the same number that fit in each tent, but with 5 fewer people. And of course, what do we see? That we require the same number of tents. And those small differences really make children attend to the effect of those individual changes. And again, children could even create their own examples to kind of extend and exemplify that. Now, for the final example, what I wanted to look at is how just these same principles have applied for me in data contexts. And essentially looking at how we can layer the information as it's presented to get children to look at structures, see possibilities, and not be too quick to have to get to the point where they have to find answers. So a way of doing that, essentially, I've taken a question, I've just covered lots up, and then created variations on those questions. So I could say, well, what could this graph represent here? What information will we see? What could it be? Or what else could it be? What couldn't it be? And we could look here at the kind of the form of a bar graph where it wouldn't be representing, for example, temperature necessarily, because that would more be represented by a line graph, but there'll be distinct groups. And then we could look, and actually it was the number of pets. There we go. And it's dog, cat, rabbit, and fish. And then I could say, well, what do you notice from here? And ask children to make specific observations. And again, this is just essentially taking a question and introducing it slowly. So there are some true or false statements in this question. There are 4 of them that we will see and we will have a look at. I wonder if you could predict what those statements could be, those true or false statements. So what could they be? And children could find different possible statements there. And then, if I want to be more directive, I could show the first part of each statement. So there are, as opposed to there are 10 more altogether, and most of, for children to predict, well, what could the rest of the statement be? What information would be required in the rest of the statement there? So let me just give you a moment to consider what they could be. And feel free, if you want longer, to pause the video. And then again, when we actually have a look at the information, and again, we've got so much more there from just one task. We hopefully then are in the position of having understood the deep structure, and we've interpreted how we need to collect that information. So again, hopefully now children having higher success. Now, let's have a look at how some of the IC reasoning resources can help out with answering worded questions. So these are all from the IC Reasoning ebook for year 3. And there's 2 read the picture examples. Now, these are all taken from either the multiplication and division section or the addition and subtraction section, those 2 combined sections. And one technique that we often use is for looking at word questions is which bar model, and can children identify the correct bar model and explain the mistake? So again, if I just give you a moment to have a look at those examples. And again, if you want slightly longer to have a look, then please feel free to do so. But again, for children to be able to identify which bar model represents the structure of the question correctly, can they explain the mistakes? Also, context questions, and for children to discern, in this instance, which one can be answered by calculating 15 divided by 5. So again, if I give you a moment to read those instances, those examples, sorry. Okay, so looking at, as I say, different structures of questions, and can children discern between multiplicative questions and questions that have an additive structure as well? And then other techniques to help children to connect information, questions, and answers. So this is one. So again, if I give you a moment to have a look at how you would join up this information. And again, if you'd like a little longer, please pause the video. But for children to figure, for example, Sam has £1. He buys 2 bananas. That's costing 30 pence. So there isn't an answer of 30 pence. So that mustn't be the question. In this instance, how much change does he get? It's 70 pence. But again, linking information, questions, answers. And then again, one final example. If I just give you a quick moment to have a read. And again, it ties in with this idea of understanding deep structures. If the question is how much does it cost and the answer is £1.80, what must the information be? And so on, and looking at those other structures, but children having to, in this instance, create the information rather than give the answer. So hopefully those resources will be really helpful as well in breaking down worded questions. Now, recapping on everything that we've covered in this session, we've looked at children predicting questions. What could the question be? And then pairing that with, well, what information will be required to answer that question? And in doing so, unpicking deep structures. And I would say that's a version of creating a numberless prompt. It's essentially, how do we look at the underlying structure of a task before children are asked to do any calculation? Now, of course, the other way around that is just removing the numbers, and for children finding different possible answers where they first have to interpret structures in a number range that they could be comfortable with. First of all, being able to interpret the information. Then we went on to looking at writing sequences of questions with small differences. So can you find them? Is that something that you could create, work towards as a staff to do that? And again, the thing that I would emphasize is if we only have small differences, children really see the effect of those differences in terms of the kind of calculation. It's like they really can link cause and effect there. Now, we talked about building visual working memory as a real precursor to a lot of things that we've done, so children can visualize the structure of mathematics in their mind's eye. And also, of course, just this ongoing thought about visual representations and how do we represent the structure of the mathematics in the way that's most appropriate? Is it with individual counters? Can we move towards bar models? Not always having to go in that route, but thinking, how do we ensure that children build up this visual picture of the underlying structure of the mathematics as the kind of key principle that I would work towards? And then again, how we deepen or open up challenges. My encouragement to you would be to think, well, to trial things out, but then take a long-term view as to how can we have a coherent approach to building children's understanding of worded questions that runs right throughout the school. So you're not having to re-establish routines or norms or ways of doing things as children come through the school. But this way of approaching worded questions is something that they are familiar with, and it becomes habitual for them to engage in these kind of maths tasks in that way. So to think about how they could predict questions. And when they do so, I've found just enormous success and growth in the children in the capacity to answer those word problems. I'd love to hear from you. Stay in touch on social media, or my email is icmaths@hotmail.com.